Hello, this is Paul from Foresight Tech. In this lecture, we're going to discuss higher derivatives. Okay, what is higher derivative? So I will introduce here. And first, the second derivative. What does the second derivative mean? Is this is the notation if we have 2 prime. Okay, this which means the second derivative. The second derivative is the derivative of the first derivative. Then we have the second derivative, right? Okay, so if we use Leibniz notation, is like this. And usually we wrote it in the first this way. And the d2y is dx2. What does this mean? Like the power of x. Like the power of x is the second derivative. And the real meaning is here. Do you remember d dx? This is the the differentiation operator, right? So which means take a derivative. Derivative of x is the first derivative. First derivative take another derivative, then we define as the second derivative. We use the notation in this way, okay? And the second derivative, that's which second derivative is the first derivative, the derivative of the first, which means the change, the rate of change, or the instantaneous rate of change of the first derivative. Okay, in the future we will come back. Okay, so we will come back to discuss what the exact meaning or the geometric meaning in the future. Okay, and how about the third derivative? We can define the second, we also can define the third, right? So the third derivative is the derivative of the second derivative. In Leibniz notation is this. Okay. Or does the second derivative take a derivative again? Okay. How about the other higher derivative, higher than 3, or fourth or fifth, so we don't put the 4 prime, okay? It's just directly put the n here, okay? Put the parentheses. Don't miss the parentheses. If we miss the parentheses, which means the power, we will put the parentheses, which means the how many, the nth derivative, okay? So the nth derivative, or we use a nth derivative to f, or we use Leibniz notation. So this is the basic definition. Let me going to see some example. So here is the very famous example in physics. Okay, derivative in physics. So let me going to see in physics if s is a position function or the distance function. Do you remember? And the instantaneous rate of change of s is instantaneous velocity, right? We discussed that problem, that classic problem. We finally find the instantaneous rate of change of the position function is the instantaneous velocity, or we simply call velocity. So velocity is the derivative of position. How about the second derivative of position? Is acceleration. So what's the acceleration? Acceleration is, we use a to describe it. A is the derivative of the velocity. Okay, if we look at the rate of change of the velocity is the acceleration. So how fast the velocity changes is the acceleration, which means as acceleration is the first derivative of the velocity. Okay, now you know the derivative of velocity is derivative of s prime, which means derivative of the first derivative of s. Therefore, is the second derivative of position function, right? Now you see the first derivative of position is velocity. The second derivative of position function is acceleration. How about the third? It's the same way. The third derivative is just what? It's just the rate of change of the acceleration. How fast the acceleration changes. That's we call it the jerk. Okay, so we go into the physics. We have velocity, acceleration, and the jerk corresponding to the first derivative of position, second derivative, and the third derivative. This is the very famous application of higher derivative. Then we're going to see one example. So here, if we give it the position function, so the question asks us to find it. Of course, this is the a position function of an object that moves in a straight line. Okay, that's the basic background. Then define the velocity functions and the acceleration functions. Do you remember? Velocity should be the first derivative, right? Acceleration should be the second derivative. That's all we need. Then we're going to see, and all we need is do calculation, right? So the first, we look at the vt first. So this is the first derivative. The definition is first derivative of position functions, and therefore we use the definition is this. I use h again. Okay, and this is delta s, right? Is t plus h minus s at t. Okay, delta y, delta x is h, and then we plug everything in. We plug that's limit a copy. Okay, so what is s? S is there. Okay, we need to evaluate s at t plus, which is this, is t plus h squared, right? And the plus t plus h, and this is the first term, and then minus the second term. Second term is t squared plus t. Okay, so this we just plug in the function, and then the bottom is h. Now we're going to simplify. So how to simplify? This should be equals to h approaches 0. Let me look at. So expand this. We have h is t square. The t square and the minus t square we cancel, right? Disappear. The second term is 2th. Okay, so left. So up here, so we have a 2 times t times h left, and then h square left also, plus h square, and this t and minus t we cancel, this h left, right? And then see, both of these already cancelled. This is the numerator, so keep in mind here is times, and then 2 over h, and then we factor the h on the bottom, on the top, and then cancel h divided out. Then we have this left. Which one we left? 2t, right? So 2 times t, and plus h plus 1. Plus 1. You already cancelled, so here we only put 1 here. Okay. Or can you look at it? This is what? This is a polynomial. So h approaches 0, put the 0 here. What do we get? We get a 2t plus 1. Equals 2t plus 1. So this is the result for the velocity functions, right? The velocity function we find. The second is how to find the acceleration. Accelerations is the second derivative, right? Okay, so let me go into see. Acceleration is this, is at, and use the definition is s 2 prime, right? Okay, the second derivative, and they use the definition is this, is h approaches 0. This means the derivative of the first derivative, if we use is the first derivative, and the t plus h minus the first derivative, right? So delta y, this is h, so make sure this is true, because this is what, if we wrote one more step, this means s prime t, right? So t, and then to put prime again, right? See, and the top is just the first prime. Exactly, you know what that means. That means the velocity, right? Now I just plug in the velocity. The first step we already found, which means this. Then we're going to see what is the velocity function. We just find the first step, the velocity function equals 2t plus 1. Okay, 2t plus 1. So the first we know is what? is 2. Now t is t plus h, of course, t plus h plus 1, right? Did the first, and then minus the second is 2t plus 1. 2t plus 1. The first step we already got this. Now what do we do? Simplify h plus 0. What do we get? So let me count to see. 2t minus 1 minus 1 minus. So we have 2h left. 2 times h and h. Of course, this equals what? This equals 2, right? The limit of 2 is 2. And this tells us the acceleration is just a constant number 2, right? So this is the results for this question. That's all. Thank you.